Welcome back to the Explainer, everyone. Today, we're taking a concept you've probably seen a million times in math textbooks and transforming it into a seriously powerful lens for understanding how our entire world works. We're talking about compound interest. But trust me, by the end of our time together, you'll see this is about so much more than just numbers on a page. Think about this for a second. What does your savings account, that car losing value in your driveway, and the booming population of a major city actually have in common? Honestly, most people would say absolutely nothing. But, as you'll see, they are all driven by the exact same underlying mathematical engine.
Okay, let's dive into this. Here's our roadmap for today. First, welcome to Stage 2. Second, playing math detective. Third, changing the compounding clock. And finally, beyond the bank.
All right, part 1. Welcome to Stage 2.
So here is that engine driving it all. Let's break down these components real quick so nobody gets lost in the jargon. A is our final amount, the destination, right? P is our principal, which is really just the starting line, the initial sum. Inside those brackets, we've got 1 plus R, that's our interest rate, divided by 100. And finally, that little n hovering up top, that's our exponent representing the number of years. This single equation right here is absolutely crucial to everything we're going to discuss today.
Now, sure, in the past, you might have calculated compound interest by painfully treating it as repeated simple interest, just dragging it out year by year. But man, that gets incredibly tedious. By simply plugging in our principal, rate, and time, we bypass all that step-by-step arithmetic and arrive directly at our final amount. It's elegant and it's super efficient.
Moving on to part 2. Playing math detective. Think about it. What if we know exactly where we ended up, the final amount, but we have literally no clue what our starting principal was? Or what if we know the start and the end, but the interest rate is a total mystery? Well, we call these inverse problems, and honestly, reverse engineering them is incredibly satisfying.
Let's kick things off with finding that starting principal. First up, we set up our trusty formula, but this time we plug our final amount in on the left side. Step 2, we just use some basic algebra to isolate P. And step 3, we just do the math. Now, what's really interesting about this example from the source is how we apply that. Let's say a sum of money amounts to $3,630 after 2 years at a 10% rate. We know our destination. By plugging those numbers into our formula and working backward across the equation, we reverse engineer the timeline to discover our starting point, our principal, was exactly $3,000.
Okay, let's step it up a notch. What if the rate is the missing piece? The logic shifts just a little bit here. First, we divide our final amount by our starting principal. Then, and this is the clever part, we have to express that ratio as a number raised to the power of n. Once those exponents match, we can drop them and simply solve for r.
So, looking at this specific example, we're asked to find the rate over 3 years. Following our steps, we divide our final amount by our starting principal and simplify that fraction down. Because our time is 3 years, we literally just have to ask, what base fraction cubed equals this result? Well, it turns out 21 over 20 cubed is the magic ratio. We drop the cubes, and we've cracked the code. The rate is exactly 5%.
Finally, the ultimate detective work, finding the time, n. We know the start, the end, and the rate, but the calendar is completely blank. Once again, we set up that amount over principal ratio. Then we take our known rate, say 10%, which gives us a base of 11/10, and we just ask ourselves, how many times do I multiply 11/10 by itself to hit our target ratio? So the crucial point here is exactly what we see in this example. 2,000 grows to 2,662 at a 10% rate. We divide the amount by the principal to get our target ratio. Since our rate base is 11 over 10, we just have to ask, how do we get the bases to match? We cube them. And because the bases are perfectly equal, we can just equate the exponents, proving that the time n must be 3 years.
All right, part 3, changing the compounding clock. This formula is incredibly flexible, but it's kind of like a seesaw. You have to obey the rules of balance. If interest is compounded half yearly, meaning twice a year instead of once, you are basically slicing that time interval in half. So to balance the equation, you have to do 2 things. You divide the annual rate r by 2, because you only get half the rate per period, but you multiply the number of years n by 2, because you have twice as many compounding periods.
Let's move to this example and see how it builds in a real scenario from the source text. Just like we talked about, the rate r gets halved and the power n gets doubled. The math just automatically adjusts itself.
Whether it's quarterly, monthly, or daily, as long as you adjust things proportionally, this engine literally never breaks down.
And that brings us to our final section, Beyond the Bank.
This is where it gets super cool, because we are no longer just talking about money. We're looking at a universal law of exponential change, and it all hinges on one tiny symbol. If something is growing, like industrial output or inflation, we use a plus sign in our formula. The amount goes up. But if something is losing value, like a machine wearing out over time, we literally just swap the plus for a minus sign. It instantly becomes a depreciation formula.
The source text explicitly shows that the exact same algebraic structure applies everywhere else. On top, we see the formula calculating the growth of industries over n years. And right below it, under depreciation, the formula is identical except for that minus sign, calculating the decreasing value of a machine. It's profound, right? Whether a factory's output is compounding upward or a machine's value is compounding downward into scrap, the math doesn't care. It governs them both perfectly.
Let's ground this in a real-world and honestly very high-stakes example, right out of our text's case studies. This isn't just theory anymore. We're looking at a critical infrastructure challenge, national blood supply. The source provides this fantastic case study based on the 2024 to 2025 period for the Indian Red Cross Society.
Get this. The data tells us they collected approximately 1.46 crore, that is 14.6 million units of blood. This massive volume represented a 15% growth from the previous year. Planners use the exact compound change formula we've been talking about to project into the future. If the donor base compounds at 15% every year, they can calculate exactly how many units they will collect in 2026 or 2027 to meet national demands.
And this brilliantly illustrates the whole point of our explainer today. We started out with a basic formula for money in a bank, but we've seen that this compound change formula is actually the invisible architect of our world. It plots industrial growth, it tracks the erosion of your purchasing power through inflation, it calculates machine depreciation, maps out the booming populations of megacities, and even projects life-saving national blood supply reserves.
So I want to leave you with this thought to ponder as we wrap up. Look around your world today. From the changing value of your car to the population of your hometown, what other elements in your life are secretly governed by the unstoppable law of compound change? Keep your eyes open, guys. The math is everywhere. Thank you so much for joining me today on The Explainer. Keep learning, keep questioning, and I'll catch you next time.